All right, let's pull back the curtain on some of the most intricate engineering feats hiding in plain sight. Have you ever tapped an app, swiped on a profile, or streamed a video and wondered about the invisible machinery making it all hum? Today, we're embarking on a truly unique deep dive, sort of a masterclass in system design, where we dissect the engineering brilliance behind everyday giants like Ticketmaster, Tinder, YouTube, and more.
What's truly captivating here is how we'll unpack these systems, one by one. We're going to examine their core components, understand the formidable challenges engineers face at massive scale, and explore the ingenious solutions they devise for reliability. Our aim isn't just to skim the surface, it's to delve into the very nuts and bolts of what makes these complex applications function. Prompts a fascinating question. How do seemingly simple user experiences transform into such incredibly robust and sophisticated architectures?
Exactly. Our mission today is to give you a shortcut to being genuinely well-informed about how these digital foundations are built. We'll start by exploring the fundamental functional needs, then confront the tricky, non-functional demands. From there, we'll identify the core building blocks, trace the high-level design, and then take a truly fascinating plunge into the deep dives, those clever, often surprising solutions to real-world engineering problems. We're going to dedicate ourselves fully to each system before moving on, ensuring you grasp every critical detail. So get ready to see the world of tech from a whole new perspective. First up, let's step into the high-stakes world of Ticketmaster. If you've ever battled for concert or game tickets online, you know the adrenaline rush. On the surface, it seems straightforward. Find a show, buy a ticket. But designing a system to handle millions of fans all hitting refresh for a single event presents monumental challenges. What's the absolute bare minimum a system like this must deliver for its users?
Well, when we talk about the functional requirements for a ticket booking site like Ticketmaster, we're detailing the core actions the system absolutely must enable. Foremost, users need to be able to view events. This is where Discover begins browsing what's available from concerts to sporting events. Equally important, users must be able to search for events, allowing them to quickly find specific artists, teams, or types of performances. And the ultimate goal, the reason the system exists, is for users to be able to book tickets to events. This crucial transaction is what everything else supports.
Okay, so that's what it does. But for a system that can face an online stampede for a popular show, how well it does those things is even more critical, right? What are the non-functional requirements that truly dictate its architecture and reliability?
This is where the engineering dilemmas truly emerge. For Ticketmaster, the non-functional requirements are paramount. The system needs to prioritize availability for searching and viewing events. Even if the booking engine is under extreme strain, users should still be able to browse what's happening. However, and this is a critical distinction, it must prioritize consistency for booking events. Imagine the chaos of two people buying the same seat that's a direct business liability. Preventing double booking is non-negotiable. Beyond that, the system absolutely has to be scalable and able to handle high throughput. Think about a major artist tour going on sale. You could have 10 million users all hitting refresh simultaneously for tickets to a single event. It's an immense, spiky load. Low latency search is also vital, ideally under 500 milliseconds, because users expect instant results when they're looking for events. And from a data perspective, the system is overwhelmingly read-heavy, with a ratio of approximately 100 reads for every one write. This means it needs to support incredibly high read throughput to constantly display event information to millions of users.
Got it. So to build such a system, you first need to define the fundamental components that make up its world, the nouns of the Ticketmaster universe. What are these core entities that the system needs to track and manage?
The core entities form the foundational data model for Ticketmaster. At the center is the event itself, which captures all the key information: date, description, type, and the associated performer or team. Then there's the user, representing any individual interacting with the system. A performer entity details the artist, company, or collective, their name, a brief description, and relevant links. The venue entity is crucial, containing its address, capacity, and most importantly, a detailed seat map that outlines the unique seating arrangements for that specific location. Our ticket entity holds all the specifics for individual tickets, the event it belongs to, precise seat details like section, row, and seat number, pricing, and its current status, whether it's available or sold. Finally, the booking entity records the details of a user's purchase, including the user ID, a list of ticket ads being booked, the total price, and the booking status, Sledgy in progress or confirmed. This entity is absolutely essential for managing the transactional aspects of ticket purchasing.
Okay, building on those foundational entities, how do different parts of the system communicate? We're talking about the APIs or system interfaces that enable clients and servers to interact and make these core actions possible.
Right. The APIs are the system's external-facing actions. We need a clear API to view event details, which is specifically designed to render the interactive seat map on the client, implying it provides granular ticket-level information. Another key endpoint is to search for events, enabling users to discover what's happening. For booking tickets, while conceptually it starts as one action in a robust design, it often evolves into two distinct endpoints, one for reserving a ticket and another for confirming the final purchase. But for a high-level overview, we can initially consider it as a single conceptual booking interface.
Let's sketch out the high-level design now. How does the system generally put all these pieces together? Let's trace the basic user flows for viewing, searching, and that crucial act of booking tickets.
All right, for users to view events, the flow begins when your client app makes a request to a URL like www.yourticketmaster.com event.eventeid. This is a standard REST GET request carrying the specific event ID. This request hits our API gateway, which handles initial routing and then forwards it to the event service. The event service then queries its dedicated events database to pull all the necessary event, venue, and performer information, packaging it up and sending it back through the API gateway to your client.
That makes perfect sense for viewing an event. But when we think about searching for events, which seems so simple to the user, what's the immediate challenge from a system perspective?
Indeed, simple on the surface, complex underneath. If the event service were to search for events based on keywords in the name, description, or other fields using a traditional like clause with wildcards in a relational database, well, it would typically require a full table scan. This approach becomes incredibly slow as the number of events grows, making it an immediate and severe bottleneck for user experience.
And what's the big picture challenge when users get to the point of actually booking tickets to events? The frustration point here must be a major design consideration.
Yeah. For booking, the primary challenge is the poor user experience that arises when someone invests time, gets to the payment page, types in all their details, only to find out the ticket they wanted just became unavailable. That race to checkout scenario can be incredibly frustrating.
This is where the engineering truly shines and where our deep dives come in. The high-level design highlights critical challenges that demand sophisticated solutions. Let's start with improving that booking experience by implementing a reservation system. How do we make sure a ticket is held for a user without double booking?
To improve the booking experience by reserving tickets, we implement a distributed lock with a time to live, TTL. We use an in-memory distributed system like Redis for this. When a user selects a ticket, our system tries to acquire a lock in Redis using a unique identifier, like the ticket ID, with a predefined TTL, let's say 10 minutes. This TTL acts as an automatic expiration time for the lock. If the user completes the purchase, we update the ticket status in the database to booked, and the application explicitly releases the lock in Redis, often before the TTL expires. However, if the TTL expires because the user didn't complete the purchase in time, Redis automatically releases the lock. This makes the ticket immediately available for other users without any additional intervention needed from our side.
That sounds incredibly clever for holding tickets. But what are the inherent challenges or trade-offs with using a distributed lock like Redis for this? Like what happens if Redis goes down?
There are indeed a few challenges. If our Redis lock system goes down, user experience for new bookings will be degraded for that period. That's true. However, it's crucial to understand that we still prevent double booking. Our underlying database will typically use optimistic concurrency control, OCC, or another similar mechanism, which acts as a final safeguard at the transactional level. The main downside is that if someone's Redis lock expires and another user snatches the ticket, the fuse user might get an error after they've filled out payment details. While frustrating, it's a better outcome than showing all tickets as unavailable, or far worse, accidentally selling the same ticket twice.
Okay, let's walk through the exact steps then. When a user wants to book a ticket, with this reservation system fully in play, how does it flow?
All right. The process begins when a user selects a seat from the interactive seat map on their client app. This action triggers a POS2 bookings request carrying the specific ticket ID associated with that seat. Our API gateway forwards this request to the booking service. The booking service's first action is to attempt to lock that ticket in our Redis distributed lock, assigning it a TTL, say, of 10 minutes. This is the duration the ticket will be held for that user. Simultaneously, the booking service writes a new booking entry into our main database, setting its status to in progress. We then send a response back to the user with their newly created booking ID and route the client to the payment page. Now, if the user stops at this point, perhaps they get distracted or change their mind. After 10 minutes, the Redis lock automatically releases, making that ticket available for another user. If they proceed, the user fills out payment details and clicks Purchase. This payment request, along with the booking ID, is sent to a payment processor like Stripe. Stripe processes the payment and then responds to our system via a webhook confirming successful payment. Our system's webhook then retrieves the booking ID that we embedded within the Stripe metadata. With this booking ID, the webhook initiates a database transaction to concurrently update both the ticket and booking tables. Specifically, the status of the ticket linked to this booking is changed to sold in the ticket table, and at the same time, the corresponding booking entry in the booking table is marked as confirmed. At this point, the ticket is officially booked.
Next, let's turn our attention to how the View Event API is going to scale to support tens of millions of concurrent requests during those popular events. This is a massive read-heavy scenario that needs incredible efficiency.
Yeah, for this immense read challenge, the solution is to aggressively prioritize caching for data with high read rates and low update frequency. This includes static or semi-static information like event names, dates, general venue information, performer bios, and static venue details such as location and capacity. To manage cache consistency and avoid stale data, we can implement two strategies. First, set up database triggers to notify our caching system of any data changes like an event date changing or a performer lineup update, which would then invalidate the relevant cache entries. Second, implement a time to live (TTL) policy for cache entries. These TTLs can be quite long for very static data like venue information and shorter for more frequently updated data, such as real-time event availability. Additionally, for robust traffic distribution, we use load balancing algorithms like round robin or least connections to evenly spread incoming traffic across our server instances.
Now, a classic point of user frustration during high-demand events, the constantly stale seat map. Users repeatedly click unavailable seats, leading to anger. How will the system ensure a good user experience with millions simultaneously booking tickets and keep that seat map accurate in real time?
You've hit on a critical pain point. With popular events, the loaded seat map becomes stale incredibly fast. The solution is to introduce an admin-enabled virtual waiting queue system specifically for extremely popular events to manage and smooth out user access during times of exceptionally high demand. Users are placed in this queue before they can even see the booking page. The process is, when a user requests to view the booking page, they're placed into this virtual queue. A WebSocket connection is established with their client, and the user is added to the queue using their unique WebSocket connection. Our system then, periodically or based on criteria like a certain number of tickets being released, dequeues users from the front of the line. These users are then notified via their WebSocket connection that they can now proceed to purchase tickets. Simultaneously, our database is updated to reflect that this user is now authorized to access the ticket purchasing system.
That's smart for managing the raw load, but how do we mitigate the frustration of long wait times in that queue, which could still lead to users abandoning the process?
Long wait times are definitely a concern. We can mitigate this by leveraging those WebSocket connections to push updates to the client in real time. By providing users with constant feedback on their queue position and estimated wait time, even if it's long, we keep them informed and engaged, reducing the feeling of being left in the dark.
Our final challenge for Ticketmaster. How can you improve search to ensure we meet our low latency requirements, especially for complex queries like fuzzy matching? A standard database lookup simply won't cut it.
To dramatically improve search and meet those low latency requirements, the solution is to integrate Elasticsearch or a similar full-text search engine. To ensure the data in Elasticsearch remains consistently in sync with our primary SQL database, we employ Change Data Capture, CDC. The system captures database changes, inserts, updates, deletes from, say, PostgreSQL, and replicates them in real-time or near real-time to the Elasticsearch index. Crucially, Elasticsearch also enables fuzzy search functionality. This is incredibly powerful for error tolerance, handling typos and slight spelling variations like Taylor Swift versus Taylor Swift, which is notoriously difficult to achieve efficiently with SQL alone.
And once we have Elasticsearch in place, how do we further speed up frequently repeated search queries and reduce the load on the search infrastructure itself?
For those highly repetitive search queries, Elasticsearch has built-in caching capabilities that can store the results. This significantly reduces the processing load on the search engine. Additionally, we can leverage content delivery networks, CDNs. By caching search results geographically closer to the user, CDNs further reduce latency and dramatically improve response times, providing a truly snappy search experience.
All right, let's pivot to something a bit more personal, or at least connection-oriented. Tinder. The swipe left, swipe right phenomenon. It seems deceptively simple on the surface, but when you consider matching millions of people in real time, there's a huge amount going on behind the scenes. What are the fundamental functional requirements a system like Tinder absolutely needs to deliver?
For Tinder, the core functional requirements are: users must be able to create a profile that includes preferences like age range and interests, and allows them to specify a maximum distance for potential matches. They also need to be able to view a stack of potential matches that align with those preferences and are within their specified maximum distance from their current location. The core interaction, of course, is that users can swipe right or left on profiles one by one, expressing yes or no on other users, and the thrilling payoff: users should receive a match notification if they mutually swipe right on each other.
Beyond those core features, the non-functional requirements are what dictate Tinder's performance and reliability. For a dating app, ensuring immediate match notifications and handling millions of daily swipes without showing stale profiles is absolutely paramount.
Precisely. The system absolutely needs strong consistency for swiping. This is critical because if a user swipes yes on someone who has already swiped yes on them, they need an immediate match notification. There can't be a delay or eventual consistency for that aha moment. The system must also scale to lots of daily and concurrent users. Think 20 million daily active users, with an average of about 100 swipes per user per day. That's billions of swipes. Loading the potential matches stack needs to happen with very low latency, ideally under 300 milliseconds, to keep the user engaged in swiping. And importantly, the system should strictly avoid showing user profiles that the user has previously swiped on to ensure a fresh, relevant experience.
What are the fundamental core entities, the building blocks, that make up the Tinder universe? It's surprisingly minimalist at its heart, isn't it?
Indeed, the core entities are quite focused. We have the user entity, representing each individual on the platform. Then there's the swipe, which is the explicit expression of yes or no on a user profile. It inherently belongs to a swiping user and is directed at a target user. Finally, the match entity signifies the successful connection between two users when they have both swiped yes on each other.
And how do these entities interact? The API design reveals the crucial actions users take within the app, from setting up their profile to actually swiping and getting their feed.
Right, the API endpoints define the user-system interactions. First, an API to create a profile is where users establish their presence and preferences. Next, we need an endpoint to get the feed of user profiles. This is how the app fetches the stack of profiles ready for the user to swipe on. Notably, there's no need to pass in additional filters like age or interests here, as it's assumed the user has already specified these in their app settings, and they can be loaded server-side. It's also worth pointing out that while you might think about pagination for this feed, it's actually superfluous for Tinder. Since it's generating recommendations, the app can simply hit the endpoint again for more profiles when the current list is exhausted rather than paging. And finally, a key API to swipe on a user. For all these requests, the user information will be passed securely in the headers, either via a session token or a JWT, a JSON web token. It's absolutely crucial to avoid passing sensitive user information directly in the request body, as this can be easily manipulated by a malicious client.
Let's trace the high-level design for Tinder's main features. How does creating a profile work? What's the initial approach for generating that stack of potential matches, and how does the fundamental swipe action flow?
Okay, to begin with creating a profile, when a user sets up their profile with preferences like age range and maximum distance, their client sends a POST request to profile with the profile information in the request body. The API gateway then routes this request to the profile service. The profile service updates the user's profile preferences in its dedicated database, and the results are returned to the client via the API gateway.
So that's profile creation. Now, what's the initial thought process and perhaps immediate challenge for users to view a stack of potential matches?
For users to view a stack of potential matches, if our profile service were to simply query the main user database for a list of users matching the current user's preferences and location, well, this query would be incredibly inefficient. Searching by location, in particular, even with basic indexing, would be exceedingly slow and become an immediate performance bottleneck at scale.
And when it comes to the core action of swiping right or left on profiles, what components are needed and what's the rationale behind separating them out?
To handle users swiping right or left on profiles, we introduced two new crucial components: a swipe service and a swipe database. The swipe service is responsible for persisting the swipe data and checking for immediate matches. The swipe database, as its name suggests, stores all this swipe data for users. The justification for this separation, having a distinct service and database for swipes, is that profile view and creation happen far less frequently than swipe rights. By separating them, the swipe service can scale up independently to handle the immense volume of daily swipes. Similarly, for the database, given the sheer volume of swipe data, a right-optimized database like Cassandra is a good fit, whereas it might not be ideal for the more structured profile data. This separation allows for independent scaling and optimization of these high-volume swipe operations.
That makes sense for separating concerns. Can you elaborate on why Cassandra specifically is a good fit for the swipe database and what trade-offs that choice brings?
Yeah, Cassandra is an excellent choice for the swipe database because of its strength in handling massive writes. We can effectively partition our data by swiping Guzarid, meaning that an access pattern to see if user A swiped on user B becomes very fast, as we can predictably query a single partition for that specific swipe in Guzarid. Cassandra's write-optimized storage engine, which leverages a commit log, mem tables, and SS tables, makes it extremely capable of ingesting high volumes of data. The primary trade-off, however, is that using Cassandra introduces an element of eventual consistency for our swipe data, which we have to account for in our match detection logic.
Given those components, when a user actually performs a swipe action, what's the sequence of events from client to server and back?
Okay, when a user swipes, the client sends a POC request to swipe. This request includes the profile ID of the user being swiped on and the swipe direction, either right or left, as parameters. The API gateway receives this request and routes it to the swipe service. The swipe service then updates the swipe database with this new swipe data. Immediately after, the swipe service checks if there's an inverse swipe already recorded in the database, meaning if the target user has already swiped right on the swiping user. If an inverse swipe is found, the swipe service returns a match notification back to the client.
Finally, the moment of truth for a dating app. How do users get a match notification if they mutually swipe on each other? This needs to be near instantaneous.
To deliver that immediate match notification, we leverage push notification services like APNS, Apple Push Notification Service, and FCM, Firebase Cloud Messaging, which have their own native APIs and SDKs for sending notifications to user devices. The typical flow is this. At some point in the past, person A swiped right on person B, and this swipe was persisted in our swipe database. Then person B swipes right on person A. Our server, upon receiving person B's swipe, immediately checks for an inverse swipe in the database, and finding that it exists, a U-matched message is displayed to person B immediately after they swipe. Concurrently, a push notification is dispatched via APNS or FCM to person A, informing them of their new match.
The real brilliance and complexity of Tinder, and where the engineering truly earns its stripes, comes in our deep dives. We need to tackle challenges like ensuring strong consistency for swipes, generating feeds with incredibly low latency, and making sure you never see the same profile twice. This is where it gets genuinely fascinating.
Let's tackle the crucial challenge of how we ensure that swiping is both consistent and low latency. It's important to first consider an alternative approach that prioritizes availability. You could solve this problem without strong consistency. You could have a background reconciliation process that runs periodically to find all matching swipes that haven't yet been processed as a match. For those, you'd simply send both person A and person B a notification. They likely wouldn't be any the wiser, assuming the other person just swiped on them in that moment. This approach effectively prioritizes availability over strict consistency for matches and represents an interesting architectural trade-off.
That's an interesting philosophical trade-off. But if strong consistency is required, if that immediate, definitive match notification is non-negotiable, how do we achieve it?
Okay, if strong consistency is a hard requirement, Redis is a significantly better fit for handling the real-time consistency needed for swipe matching logic than Cassandra. While Cassandra excels at durability and storing vast amounts of data, it's not designed for the kind of atomic operations necessary for immediate match detection. Instead, we would use Redis for those atomic swipe operations, with Cassandra still serving as our durable, long-term storage layer. To ensure that related swipes between the same two users always land on the same Redis shard, we'd use keys that combine both user IDs in a consistent, canonical way. By leveraging Redis's atomic operations via Lua scripts, we can bundle swipe recording and match checking into a single, indivisible operation. This ensures the necessary consistency and maintains very low latency due to Redis's in-memory nature. The system then scales horizontally by adding more Redis nodes, with consistent hashing ensuring related swipes stay together.
Lua scripts sound powerful for ensuring atomicity. Can you briefly explain what they are and why they're so critical here?
Yeah, Lua is a lightweight, fast scripting language often embedded in applications. In Redis, Lua scripts are used to run atomic transactional operations directly on the Redis server. While individual Redis commands are atomic, a Lua script allows you to bundle multiple operations together and execute them as a single atomic unit. For example, when user A swipes right on user B, our goal is threefold. First, save A's swipe on B. Second, check if B already swiped on A. And third, if they did, declare a match. Without Lua, running these steps as separate commands could lead to race conditions if another user's swipe interjects. With a single Lua script, a single Redis client call ensures all three operations happen together safely without any interference, guaranteeing strong consistency.
What are the challenges with relying on Redis for this real-time atomic operation, and how does Cassandra still play into ensuring overall data durability?
The main challenges with Redis involve carefully handling node failures and the rebalancing of the consistent hashing ring. However, because Cassandra is our durable, long-term storage layer, we can be quite aggressive about expiring data from Redis. We can periodically flush all swipe data to Cassandra and only maintain a rolling window of recent swipes in Redis. This means if we ever lose Redis data due to a node failure, we primarily lose only the ability to detect matches for very recent swipes. Users can always swipe again, and the complete historical record of swipes remains safe in Cassandra. This hybrid design beautifully combines Redis's strong consistency and atomic operations for real-time match detection with Cassandra's durability and massive storage capabilities for historical data, resulting in a highly available and scalable system that meets the core requirement of consistent, immediate match detection.
Next up, the challenge of low latency for feed stack generation. Users expect an endless stream of fresh profiles with no lag. How do we ensure that snappiness?
The optimal solution is to cleverly combine the benefits of both pre-computation and real-time querying using an indexed database. We would periodically pre-compute and cache user feeds based on their preferences and locations. When a user opens the app, they immediately receive this cached feed, allowing for instant interaction without any delay. As users swipe through and eventually exhaust their cached feed, the system seamlessly transitions to generating additional matches in real time. This is achieved by leveraging a powerful index database like Elasticsearch. By creating robust indexes on fields commonly used in feed generation, such as user preferences, age range, and crucially, geospatial data like location, we can significantly speed up real-time query response times. The infinite stack illusion is maintained by triggering a refresh of the stack when a user has just a few profiles left to swipe through.
But caching often leads to stale data. How do we ensure we avoid stale feeds and that users aren't seeing outdated profiles?
To prevent stale feeds, we implement a strict TTL, time to live, for cached feeds, perhaps less than 1 hour, and then recompute these feeds via a background job on a fixed schedule. Also, to conserve resources, we might only pre-compute feeds for truly active users rather than all registered users. It's also critical to consider user-triggered actions that can lead to stale profiles in the feed. For instance, if the user being served the feed changes their filter criteria, or if they change their location significantly by moving to a different neighborhood or city. In these cases, the cache feed immediately becomes stale and needs to be regenerated or updated promptly.
Next, a critical user experience point. How can the system avoid showing user profiles that the user has previously swiped on? Nobody wants to see the same person twice if they've already made a decision.
For users who have accumulated very large swipe histories, say beyond a certain threshold that would make storing all their past swipes in a traditional cache unwieldy or contains checks too slow during a query, we can consider using a Bloom filter. A Bloom filter is a probabilistic data structure that can tell us with a high degree of certainty if an element is not in a set, and with some probability if it is in the set. Here, we would build and cache a Bloom filter for that user and use it in the profile filtering process. When a profile is considered for the feed, we check its ID against the Bloom filter of previously swiped profiles. A Bloom filter would sometimes yield false positives for swipes, meaning it might indicate that a user has swiped on a profile they actually haven't. However, and this is key, the Bloom filter would never generate false negatives, meaning it would never say a user hadn't swiped on a profile they actually did swipe on. This ensures we successfully avoid re-showing profiles that have genuinely been swiped on, though a small number of profiles might never be shown to the user due to those rare false positives.
Is there an alternative solution for avoiding showing previously swiped profiles, perhaps one that leans more on the client side?
Yes, an interesting alternative is to leverage client-side swipe cache notes. The approach here is to use a client-side cache, perhaps storing the most recent swipes to filter profiles. This design choice explicitly avoids relying on a back-end cache, which can introduce its own NoSQL availability issues. In terms of functionality, the client itself stores a record of recent swipes and actively filters out any already swiped profiles from the incoming feed. When the client reaches a threshold of, say, 150 to 200 prefetched profiles, it pings the backend for a new feed, requests it, and then applies its client-side filter to that new list. This approach makes a key assumption that the user primarily operates on a single device, which enables efficient client-side data management. The benefits are significant. It reduces backend cache costs, helps maintain feed relevance, and supports efficient profile prefetching for a smoother user experience.
Next, let's zoom out to a massive scale. How does YouTube figure out its top K videos? Those trending videos, the heavy hitters. This isn't just about counting clicks, it's about real-time aggregation across billions of views. First, why would a company even need this, and what are the primary goals?
Well, the use case for identifying top K videos or heavy hitters is incredibly broad across many industries. A search engine, for instance, would need to index this data and rank it, perhaps using sophisticated algorithms like PageRank to identify authoritative or popular content. On a different note, a company like OpenAI might ingest the raw text extracted from these popular pages into a database, leveraging it to train powerful large language models. In terms of functional requirements, the system must enable clients to query the top key videos with a maximum limit of 1,000 for a given time period. These time periods should be clearly defined and limited to specific intervals, the last 1 hour day, month, and an all-time ranking.
And the non-functional requirements are where the true challenges emerge for such a high-volume system. Just think about the sheer number of views YouTube handles daily.
Indeed. Scalability is paramount. The system must gracefully handle continuous increases in data volume, potentially up to millions of requests per second, without breaking a sweat. Availability is also critical. It needs to be resilient to hardware failures and network partitions, ensuring this trending data is always accessible when users query for it. For a near real-time experience, low latency is essential. Retrieving that top K list should happen in mere tens of milliseconds. And finally, accuracy is vital. The results should ideally be precise, counting every single event rather than relying on sampling, which could skew popularity rankings.
Let's put some numbers to that. What kind of scale estimation are we talking about for throughput and storage for a system like YouTube? It's mind-boggling.
For throughput, if we estimate 70 billion views per day and divide that by approximately 100,000 seconds in a day, that translates to a staggering 700,000 transactions per second. When considering storage, let's estimate video uploads. If we have 1 hour of content uploaded per second and each video averages 6 minutes of content multiplied by 100,000 seconds per day, that results in about 1 million videos uploaded per day. Over a decade, that's 1 million videos per day multiplied by 365 days per year for 10 years, equaling a massive 3.6 billion videos. For a naive storage approach, say a simple table of IDs and counts for 4 billion videos, with 8 bytes for each ID and 8 bytes for each count, that would amount to approximately 64 gigabit. This illustrates the sheer scale of the data involved.
Given those functional needs and massive scale, the API or system interface for querying top videos is surprisingly simple. What does that look like?
Yeah, the API for querying the top videos is straightforward. A standard GET-TO request to viewstop.window. This allows clients to specify the desired time window, whether it's the last hour, day, month, or all time, and the number of top videos God they wish to retrieve. The core entities we're interacting with here are the video itself, each individual view event, and the specific time window for which the top K are being calculated.
Now let's explore the high-level design. The most intuitive, naive approach to counting views and maintaining a top list sounds simple, but it quickly runs into major issues at this scale. So how would one initially conceive of this, and what are its primary shortcomings?
The naive approach is quite intuitive. When a view request comes in, we atomically increment a counter for that video ID within a hash table. We then retrieve that updated count and compare it against the smallest element, or floor, of a min heap that holds our current top K videos. If the new count is higher than the heap's floor, meaning this video now belongs in the top K, we update or insert it into the heap and then re-heapify. Clients would then simply query directly from this heap to retrieve the top K videos. However, the primary issues with this approach are twofold. First, maintaining reliability in the presence of failures. What happens if the server holding the hash table or heap crashes? And second, scaling the right throughput of the single system that's processing all those increments. To address these, a first step is to maintain multiple replicas of our counter instances and periodically snapshot their memory state. This allows us to recover quickly in case of failure by loading the most recent snapshot and then rereading from the incoming data stream until we've caught up to the current state.
This is where the real engineering cleverness comes in, and where our deep dives truly begin. How do you handle the complexities of time windows, massive incoming requests, partitioning data for scalability, the challenges of unbounded streaming data, and making those crucial trade-offs with approximate data structures?
Okay, let's tackle how to handle time windows for views, like the last minute, hour, or month, alongside an all-time count. We begin by processing all raw view events from a central stream, like a Kafka topic. When a view occurs effectively a rising edge event, it adds 1 to the count for all relevant time windows. Example, if it's a new view, it counts for the 1 hour, 1 day, 1 month, and all time windows. To remove outdated views as time progresses, we employ falling edge pointers. These are delayed markers positioned by each window's duration, for example, 1 hour for the 1 hour window, that subtract views as they fall outside the current window. For example, if video A gets a view at T0.05, it increases all current counts. But by T1.05, the 1 hour window's falling edge will trigger removing A's view from the 1 hour count, while its contributions to the day and month counts remain unchanged. This means we'd effectively maintain separate counters and top K lists for each time window. While this approach increases storage by about 4x for hour, day, month, all time, it ensures highly accurate counts for each specific window. Consider views for video A at T0.05 and video B at T0.2 and T0.40. For the 1 hour window, we'd see A1, B2 at T equal 0.40, but it would become empty by T1 1.40 as those views expire. For the 1 day and all time windows, they would both still show A1, B2 at T.40, with the 1 day count only dropping A's view much later at T24.05.
What are the trade-offs or challenges with this time-windowed counting approach?
Well, the challenges include the need for our Kafka stream to retain data for at least a month, which significantly increases storage costs for the messaging layer. It also results in higher read loads as we're now querying and managing multiple distinct counters. Furthermore, our top lists for each window need to be provisioned with extra capacity, perhaps 2,000 entries instead of 1,000, to efficiently manage the dynamic inflow of new views and the simultaneous expiration of older ones.
Moving to our next deep dive. How do we handle the incredibly large number of incoming requests efficiently, given that a view needs to be tabulated within roughly a minute of it happening?
Given that we have approximately a 1-minute latency requirement from when a view happens to when it needs to be tabulated, the most straightforward solution is to introduce a cache. We can set a 1-minute TTL, time to live, on this cache, which guarantees that our results are never more stale than our requirement. When a query for top videos comes in, we first check the cache. If the results are present and not expired, they are served immediately from cache. If not, or if the cache entry is stale, we query all the underlying counter instances and their associated heaps that contribute to the request's specific time window. We then merge these values, calculate the new top K, and store these merged values back in the cache for subsequent requests, reducing the load on our back-end processing.
For massive scalability, we often talk about partitioning data. How is data partitioning used to distribute the load for such a high-throughput system?
To effectively address the memory and throughput issues that arise at massive scale, we partition our data based on item keys, such as video IDs. A specialized component, often called a data partitioner, is responsible for routing each incoming event to its respective processor host. This ensures that each processor host stores view counts only for a manageable subset of the total items. These individual processor hosts then independently compute their local top K heavy hitters for their assigned subset of videos, using the hash table plus heap approach we discussed earlier. The final step involves a merging phase where these individual local top K lists are combined into a single global top K list. This is a classic problem of merging and sorted lists. The benefits are clear. Throughput and memory load are distributed across multiple machines, drastically improving scalability. Also, the global top K computation now works on small, manageable data chunks, the local top K list, rather than trying to aggregate from entire, massive frequency tables.
What are the inherent complexities that data partitioning introduces, especially when dealing with dynamic data?
Data partitioning definitely introduces complexities. You have to consider data replication for reliability, ensuring that if one processor node fails, its data isn't lost. There's also the challenge of rebalancing when new nodes are added or old ones removed to redistribute data evenly. And a perennial issue is handling hot partitions, where an uneven distribution of popular videos or events can cause a single partition to become overloaded. Furthermore, this partitioning approach works best for bounded datasets, meaning fixed time windows, rather than truly continuous, unbounded streams.
That brings us to the unique challenges of streaming, unbounded data. How do you manage that when it's impossible to maintain full counts indefinitely for every video ever?
Unlike fixed-size datasets, streaming data is by its nature unbounded and continuous, making it impossible and impractical to maintain full, precise counts for every video indefinitely. Our system solution to this involves our processor hosts maintaining memory aggregated counts for only short periods, typically just 1 minute. After this minute, they flush their local top K lists to a dedicated storage service. This storage service then accumulates these per-minute top K intervals, which allows for very efficient retrieval of approximate top K data for small time windows. However, a critical point here is that calculating precise heavy hitters over longer intervals, such as an hour or a day, based solely on these summarized sub-interval lists, is inherently approximative and imperfect. The only truly precise way to get accurate top K results for large time spans involves processing all the raw data for the entire period, which, as you can imagine, is a highly resource-intensive task. To resolve this trade-off, the system must, first, store raw event data on disk, usually in a distributed file system like HDFS or cloud storage like S3. Second, use MapReduce or similar batch processing frameworks to perform those heavy calculations offline and produce precise counts and final top K lists for those longer aggregated windows. This forms our slow path.
Finally, how do we make those crucial trade-offs with approximate data structures to overcome scalability constraints without holding every single count in memory? This sounds like a clever compromise.
To overcome the scalability constraints without having to hold all counts for all videos in memory indefinitely, approximate data structures offer an elegant compromise. A prime example is the count-min sketch. This is a fixed-size, two-dimensional array defined by its width and height, where the height typically corresponds to the number of distinct hash functions used. For each element insertion, each video view, multiple hash functions update corresponding counters within the sketch by incrementing their values. To estimate the frequency for a particular element, a video's view count, you take the minimum value across all its associated counters determined by the hash functions. This minimum approach helps to mitigate overestimations that can occur due to hash collisions. The primary advantages are significant. It uses fixed memory irrespective of the dataset size, directly addressing memory bottlenecks. It also provides a probabilistic count with tunable accuracy based on the sketch's dimensions. Applying this to our problem, we would replace the full exact hash tables on our processor host with these count-min sketches. We would then use a min heap to track the top K heavy hitters, now with their approximate counts. This allows for rapid, highly scalable computation that, yes, sacrifices some absolute accuracy for immense gains in performance and memory efficiency.
Okay, let's zoom out now. When you put all these components and ingenious solutions together, what does the overall high-level system architecture look like for a massive top K video feature at YouTube scale? This is a complete picture.
The complete solution architecture effectively combines multiple components, operating synergistically in both a fast and a slow data path. For data ingestion, client events such as video views first pass through an API gateway. This gateway not only manages requests, but also generates detailed logs that capture these events. These logs then serve as the initial data source, either handled by background processes or directly streamed further into the system. Initial in-memory data aggregation can even occur at the API gateway level if resources permit, using simple hash tables for preliminary counting. From there, these aggregated data points or messages enter a messaging layer, typically a distributed messaging system like Apache Kafka. Kafka is crucial here because it partitions data streams across multiple hosts, enabling parallel processing downstream. Now, the paths diverge. The fast path is dedicated to approximate real-time processing. Here, fast processor hosts continuously consume messages from Kafka, rapidly updating their count-min sketches for very short intervals. These sketches quickly aggregate the data. Count-min sketches from multiple fast processors are then merged by simply adding their corresponding cells. The results are intermittently flushed to a storage service, which provides low-latency access to these approximate top K lists for small time windows, ranging from seconds to minutes. Replication in this fast path can be minimal, as slight data loss or approximation is generally tolerable for real-time trending data. In parallel, the slow path focuses on precise batch processing for long-term accuracy. Here, a data partitioner reads the raw events from the messaging layer and intelligently distributes them to specific partitions, ensuring proper routing and load balance. Partition processors then aggregate detailed exact counts in memory over longer windows, for instance, 5-minute intervals, batching these granular results into files. These files are stored in a distributed file system like HDFS or S3. This enables subsequent heavy batch processing using MapReduce jobs. The first MapReduce job aggregates exact frequency counts across all raw data, and a second job computes the precise top K heavy hitters by efficiently partitioning, mapping, and reducing these partial results. This slow path yields highly accurate top K results, but with longer latencies, typically ranging from minutes to hours. Finally, for data retrieval, the API gateway exposes a unified TopK API that queries our storage service. For short intervals, it returns approximate results by merging multiple interval sketches from the fast path. For longer intervals that perfectly align with our batch processing window, such as hourly aggregates, it serves the precise results directly from the slow path. For any intermediate intervals, it performs approximate merges of results from differing granularities, though of course the precision diminishes slightly in those cases.
This isn't just theoretical. These principles were applied across the industry. Where else do we see these heavy hitter detection strategies in action in the real world?
Oh yeah, we see these heavy hitter detection strategies implemented in countless real-world applications. Beyond YouTube tracking views for its trending videos, Google extensively uses them to process search queries for identifying trending keywords in real time. Twitter employs similar techniques for tracking top hashtags and determining what's currently popular in retweets. Spotify leverages these strategies to identify the most played songs globally or within specific regions. And crucially, in cybersecurity, these systems are indispensable for detecting DDoS attacks by rapidly identifying heavy-hitter IP addresses that are flooding network traffic, allowing for quick mitigation.
From global video trends, let's shrink down to something seemingly simple but surprisingly complex. A URL shortener like bit.ly. Turning a long, unwieldy link into a compact, shareable one. What are the basic functional requirements it needs to fulfill?
For a URL shortener like bit.ly, the functional requirements are deceptively simple, yet foundational. Users need to be able to submit a long URL and receive a shortened version in return. Optionally, users should be able to specify a custom alias for their shortened URL, allowing for more memorable links. Another optional feature is for users to be able to specify an expiration date for their shortened URL, after which it will no longer redirect. And fundamentally, the system must allow users to access the original URL by using the shortened URL that's the core utility of the service.
And like any system expected to operate at scale, the non-functional requirements are critical. For a URL shortener, uniqueness of those short codes, the speed of redirection, and extreme reliability are paramount, especially given how read-heavy such a service would be.
Absolutely. The system must absolutely ensure uniqueness for the short codes. No two long URLs can ever map to the same short URL, or you'd have chaos. The redirection itself needs to occur with minimal delay, ideally under 100 milliseconds for a seamless user experience. The system must also be highly reliable and available 99.99% of the time, prioritizing availability over strict consistency, because a broken link is a bad experience. And critically, it needs to scale to support 1 billion shortened URLs and 100 million daily active users. It's important to note the read-to-write ratio here. It's heavily skewed towards reads, approximately 1,000 reads for every one write. Users frequently click shortened URLs while the creation of new ones is comparatively rare.
What are the core pieces of information, the core entities that a URL shortener needs to keep track of to make this service work?
The core entities for a URL shortener are quite lean. We have the original URL, which is the full long URL that the user wants to compact. Then there's the short URL, which is the compact shortened version that the user receives and can easily share. And finally, the user entity, representing the individual who initiates the shortening process and owns the specific shortened URL.
And how do you interact with such a system? The APIs or system interfaces define the simple yet powerful actions of shortening and redirecting URLs.
The API surface for a URL shortener is quite minimal and focused. You primarily need an API to shorten a URL, which would typically be a POST shortened endpoint where a user sends the long URL and the system responds with the generated short one. And then fundamentally, you need an API to redirect to original URL. This is typically a GT shortcode endpoint. When a user or browser hits this shortcode, the system looks it up and issues an HTTP redirect to the original long URL.
Let's lay out the high-level design now. How does a long URL get transformed into a shortened version, and then how does that shortened URL seamlessly redirect to the original?
To explain how users submit a long URL and receive a shortened version, the process starts when our primary server receives the request and begins validating the incoming long URL. For this validation, we can use popular open source libraries like is_url or develop a simple custom validation logic. Next, the system queries its database to check if that specific long URL has already been shortened previously. If the URL is valid and it doesn't already exist in our system, we proceed to generate a unique short URL. Once generated, the short URL, including its unique shortcode, or custom alias if provided, the original long URL, and any specified expiration date is inserted into our database. Finally, the newly created short URL is returned to the client.
And how about the other side of the coin? Users accessing the original URL by using the shortened one. What kind of HTTP redirects are involved, and why might one be preferred over another?
For users to access the original URL using the shortened one, the system issues an HTTP redirect. There are two common types. A 301 permanent redirect tells browsers to cache this response, meaning subsequent requests for the same short URL might go directly to the long URL, bypassing our server entirely. A 302 temporary redirect, on the other hand, instructs browsers not to cache the response, ensuring that future requests for the short URL will always go through our server first. The 302 redirect is often preferred for URL shorteners because it provides more control over the redirection process, allowing for future changes or deletions of the short URL, and crucially, it enables the collection of click statistics for each short URL, which is vital for analytics.
Now for the deep dives. The real challenge here is ensuring absolutely unique short URLs, making those redirects incredibly fast and scaling to billions of URLs and millions of daily active users. These aren't trivial problems for such a seemingly simple service.
Okay, to begin with how we ensure short URLs are unique. A robust and highly scalable solution is to simply increment a counter for each new URL. The output of this counter, which is a plain number, can then be encoded using base 62 encoding, using characters 0, 9, AZ, AZ, to ensure a compact and human-readable representation. Redis is exceptionally well suited for managing this counter. Being single-threaded, Redis processes one command at a time, inherently eliminating race conditions for our incr command, which is atomic, and guarantees the increment operation executes completely without interference. The challenge, of course, is that in a distributed environment, maintaining a single global counter can be tricky due to synchronization issues across all instances of our primary server needing to agree on its value. To give you a sense of scale, the number 1 billion encoded in base 62 is only 15-foot GG. This means that even with a billion URLs, our shortcodes would still be quite compact, using just 6 characters. As the system approaches 62 to the power of 7, which is over 3.5 trillion possible URLs, we would then need to move to 7-character codes.
Once a shortened URL exists, how do we ensure that redirects are lightning fast for a seamless user experience? That 100 meters target is pretty aggressive.
To ensure redirects are lightning fast, we employ 2 primary strategies. First, extensive caching. We introduce an in-memory cache, like Redis or memcached, between our application server and the database. This cache stores frequently accessed mappings of shortcodes to their corresponding long URLs. When a redirect request comes in, we first check the cache. If the mapping is there, we serve it immediately, avoiding a slower database lookup. Second, and critically, we leverage CDNs, content delivery networks, and edge computing. This allows redirect requests to be handled geographically much closer to the user's location. For the most popular shortcodes, the redirection can actually happen directly at the CDN's edge node, effectively never even needing to reach our primary server. This drastically reduces latency and improves response times for a global user base.
Finally, the big picture. How do we scale to support 1 billion shortened URLs and 100 million daily active users? This sounds like an enormous amount of data and traffic. What are the database considerations, and how do we handle the core counter in a distributed fashion?
Let's break down the database needs first. Each row in our database would consist of the short code approx. 8 bytes, the long URL around 100 bytes, creation time 8 bytes, an optional custom alias 100 bytes, and expiration date 8 bytes. This totals to about 200 bytes per row. Rounding up to 500 bytes per row accounts for additional metadata like creator-ID or analytics-ID. For 1 billion mappings, that's 500 bytes multiplied by 1 billion rows, which equals 500 gigabytes of data. The good news is, this volume is well within the capabilities of modern SSDs. Any reasonable database technology, PostgreSQL, MySQL, or a NoSQL solution like DynamoDB should be sufficient for the core storage. When considering database availability, if our primary database goes down, we'd implement database replication, creating multiple identical copies on different servers. If one fails, traffic is redirected to another. We also need a robust database backup system to periodically snapshot our data to a separate, durable location. Now, a crucial point. Since reads are far more frequent than writes, 1000.1 ratio, we can significantly scale our primary server by separating read and write operations. This naturally leads to a microservice architecture where a dedicated read service handles all incoming redirects, while a write service is responsible for the creation of new short URLs. This separation allows us to scale each service independently based on its specific demands.
But what about our counter for unique shortcodes, which we said was crucial earlier? How does that work in this new distributed write service setup?
That's a great question about the counter in a distributed setup. Instead of each write service instance hitting Redis for every single increment, we can optimize this. Each write service instance would request a batch of counter values from our centralized Redis instance, for example, requesting 1,000 values at a time. The Redis instance would then atomically increment the global counter by 1,000 and return the start of that batch to the requesting write service. This write service instance can then use those 1,000 unique values locally without needing to contact Redis for each new URL. Only when that batch is exhausted does the write service request a new one. This approach significantly reduces the load on Redis and network calls, improving overall performance while still guaranteeing uniqueness across all instances. For Redis itself, we'd use its built-in replication features, like automatic failover and cross-region replication offered by Redis Enterprise for high availability. And for additional durability of that critical counter, its value can be periodically persisted to a more durable storage system.
From static links, let's jump into real-time movement and coordination. Uber. This is the ultimate example of orchestrating drivers and riders dynamically, where location, time, and availability collide at massive scale. What are the essential functional requirements an Uber-like service must deliver?
The functional requirements for a ride-sharing service like Uber are all about connecting demand with supply in real time. Riders first need to be able to input a start location and a destination and get a fare estimate. Once they have that, they must be able to request a ride based on the estimated fare. Upon request, a critical function is that riders should be matched with a driver who is nearby and available. And from the driver's perspective, they must be able to accept or decline a request and then navigate to both the pickup and drop-off locations.
And for such a real-time, location-dependent service, the non-functional requirements are incredibly demanding. We're talking about low latency matching, strong consistency for assignments, and high throughput during those critical peak hours.
You're absolutely right. The system must prioritize low latency matching, aiming for a match or a clear failure indication in under 1 minute. This speed is crucial for user experience. Crucially, the system must ensure strong consistency in ride matching. We cannot have a single driver assigned to multiple rides simultaneously. That would be disastrous. Furthermore, the system needs to handle high throughput, especially during peak hours or special events. Imagine 100,000 ride requests originating from the same location concurrently. The system must absorb and process that without collapsing.
What are the fundamental pieces of information that Uber needs to manage to make its service work? The core entities are crucial here, defining the universe of a ride-sharing platform.
The core entities define the data model for Uber's operations. The rider entity holds personal details like name and contact information, plus their preferred payment methods. The driver entity includes personal details, vehicle information, make, model, year, preferences, and their availability status. The fare entity encapsulates the pickup and destination locations, the estimated fare, and the estimated time of arrival for a proposed trip. The ride entity captures all pertinent details of an actual trip, the identities of the rider and driver, vehicle specifics, the current state of the ride, the planned route, the actual fare charged at the end, and critical timestamps for pickup and drop-off. Finally, and uniquely important, the location entity stores the real-time geographic coordinates, latitude and longitude of drivers, along with a timestamp of their last update.
The APIs, or system interfaces for a ride-sharing service, reveal a fascinating real-time dance between riders and drivers. Security is also a huge consideration here, especially with sensitive user and fare data.
Indeed, the APIs orchestrate this dance. We have a PS fare endpoint for riders to get a fare estimate. Then, a request ride endpoint, typically a PS rides, which initiates the creation of a ride object. For keeping track of drivers, there is an update driver location endpoint, usually a PUSO driver's location, which returns a success or error. Now, here's a critical security point. The driver aid should always be present in the session cookie, or JWT, JSON Web Token, and never directly in the requested body or path parameters. More broadly, you should never pass sensitive or server-generated data like user aid, timestamps, or even fare estimate in the body or query parameters. This is a fundamental red flag indicating a lack of understanding of security best practices. User data should exclusively come from the session, or JWT, timestamps must be generated by the server, and data like fare estimate should be retrieved from the database, never trusted from the client. Finally, an accept ride request endpoint, typically a petch rides.rideid, allows a driver to update the ride object by accepting it.
All right, let's trace the high-level design for how a rider gets a fare estimate, requests a ride, gets matched with the driver, and how that driver then accepts the request. This is the core operational flow of the Uber service.
Okay, for riders to get an estimated fare, a rider enters their pickup and destination into the client app, which sends a POST request to our backend via the fare endpoint. The API gateway receives this request, handles authentication and rate limiting, then forwards it to the ride service. The ride service, in turn, makes a request to a third-party mapping API, like Google Maps, to calculate distance and travel time. It then applies the company's dynamic pricing model to generate a fare estimate. The ride service creates a new fare entity in its database with these details, and finally returns the fare entity back through the API gateway to the rider client, allowing the rider to decide whether to accept and proceed.
Once a rider has that estimate, what happens when they decide to request a ride based on that fare?
To request a ride, the user confirms their request in the client app, sending a POST request to our backend with the ID of the fare they are accepting. The API gateway again handles authentication and rate limiting, forwarding to the ride service. The ride service receives this, creates a new entry in the ride table, linking it to the accepted fare, and crucially, initializes the ride's status as requested. At this point, it triggers the complex matching flow to assign a driver.
And that's where the real magic or complexity begins. Matching a rider with a nearby and available driver. How does that unfold at a high level?
While the rider is requesting, in parallel, drivers are constantly sending their current location to a dedicated location service. This service updates our database with their latest latitude and longitude, allowing us to track their precise position in real time. When the matching workflow is triggered by a ride request, it leverages these constantly updated driver locations to query for the closest available drivers, actively searching for an optimal match based on proximity and other factors.
Finally, once a match is found, how does the driver actually accept or decline request and then navigate to pickup drop-off?
After the ride matching service identifies and ranks eligible drivers, it sends a notification to the top driver on that list, typically via APN or FCM. The driver receives this notification for a new ride request. They open their driver client app and can either accept or decline. If they accept, the app sends a PDTCH request back to our backend system with the ride ID. If they decline, the system will send the notification to the next driver on the ranked list. When the API gateway receives the driver's response, it routes it to the ride service. The ride service updates the ride's status to accepted in the database and assigns the driver. It then returns the pickup location coordinates to the driver client. With these coordinates, the driver uses their on-client GPS to navigate to the pickup location and eventually the drop-off.
Now for the deep dives that transform this high-level flow into a truly robust, real-time system. How do you manage constant driver location updates, prevent double assignments, ensure requests aren't dropped, and scale this whole intricate dance to a global level? This is where the geospatial magic and distributed systems really shine.
Let's first address how we handle frequent driver location updates and efficiently search proximity on that location data. We're solving two major problems here. The sheer high frequency of writes, millions of drivers updating their location every few seconds, and query efficiency, the need to quickly find drivers within a given radius. The most effective solution is to use an in-memory data store like Redis, which specifically supports geospatial data types and commands. This allows us to handle the high volume of real-time driver location updates and perform proximity searches with exceptional throughput and low latency. Redis also minimizes storage costs by automatically expiring data based on a specified time to live, TTL, meaning we only retain the most recent location updates.
Given Redis is in memory, what are the challenges regarding its persistence for such critical real-time location data?
Since Redis is primarily an in-memory data store, there is an inherent risk of data loss in the event of a system crash or power failure. To mitigate this, we can enable Redis persistence mechanisms like RDB, Redis database, which takes periodic snapshots of the in-memory data to disk, or AOF, append-only file, which logs every write operation. For even higher availability, we'd use Redis Sentinel. Sentinel provides automatic failover if the master node goes down, ensuring a replica is promoted to master seamlessly. Even in the worst-case scenario of a system failure, the impact would be minimal. Since driver location updates are frequent, coming in every 5 seconds, it would only take that long to recover and rebuild the system state to current accurate locations.
Beyond just the data store, how do we manage system overload from frequent driver location updates while still ensuring sufficient location accuracy? There must be a smarter way than just constant pings.
To manage that system overload while maintaining accuracy, we implement adaptive location update intervals. This dynamically adjusts the frequency of location updates based on contextual factors. For example, a driver speeding down a highway might update less frequently than a driver idling at a pickup point. Other factors include direction of travel, proximity to pending ride requests, and the driver's current status, for example, active, offline. This strategic adjustment allows us to significantly reduce the overall number of location updates, thereby alleviating system load while still maintaining the necessary accuracy for matching and navigation.
A critical challenge in ride-sharing is preventing multiple ride requests from being sent to the same driver simultaneously. That would be a nightmare scenario. How do we ensure that strong consistency for driver assignments?
To prevent multiple ride requests from being sent to the same driver simultaneously, we again leverage a distributed lock with an in-memory store like Redis. When a ride request is dispatched to a driver, a lock is immediately created in Redis. This lock uses a unique identifier, such as the driver ad, and is set with a TTL, time to live, corresponding to the acceptance window duration, perhaps 10 seconds. The ride matching service attempts to acquire this lock on the driver ad. If the lock is successfully acquired, it means no other service can send a ride request to that specific driver until the lock expires or is explicitly released. If the driver accepts the ride within that 10-second TTL window, the ride matching service updates the ride status to accepted in the database, and the lock in Redis is released. If the driver doesn't accept within the TTL, the lock in Redis automatically expires, making them available for another request.
How can we ensure no ride requests are dropped during peak demand periods, even if core services go down? This points to a resilient queuing system.
To ensure new ride requests are dropped, especially during peak demand, we implement a queuing system with dynamic scaling. When a ride request comes in, it's immediately added to this queue. The ride matching service then processes requests from this queue. We use a distributed message queue system like Kafka. The key here is that we only commit the offset of the message in the queue after a match has been successfully found and confirmed. This means if the ride matching service instance goes down mid-processing, the match request remains in the queue, and a new instance of the service will automatically pick it up and reprocess it, ensuring no request is lost. A standard FIFO first-in, first-out queue could, however, lead to requests getting stuck behind one that's taking a very long time to process. This can be addressed by instead using a priority queue, allowing us to prioritize requests based on factors like driver proximity, driver rating, or other relevant business logic, ensuring more urgent requests are processed sooner.
Finally, how can you further scale the entire system to reduce latency and improve throughput on a global level? This is where the sheer distributed nature of Uber truly comes into play.
To further scale the entire system for reduced latency and improved throughput globally, the most effective approach is pervasive horizontal scaling by adding more servers. This is achieved by sharding our data geographically, meaning we partition our data based on regions or cities. Alongside this, we utilize read replicas to improve read throughput by distributing read loads across multiple copies of our data. This principle of geographical sharding and replication applies across every component of our architecture, from our microservices to our message queues like Kafka, and especially our databases. To manage the inherent complexity of sharding and managing numerous servers, we would employ consistent hashing to distribute data evenly across shards, and implement a robust replication strategy to ensure data is mirrored across multiple servers, providing both load distribution and crucial fault tolerance.
Now let's dive into the fascinating world of web crawlers. These are the unsung heroes that power search engines and increasingly train large language models by systematically exploring the vastness of the internet. What are their core functional requirements?
Well, the primary use case for a web crawler is diverse and foundational. A search engine, for instance, would utilize the crawled data to index the web and rank pages, often employing sophisticated algorithms like PageRank to determine content authority. On the other hand, a company like OpenAI would likely dump the raw text extracted from these crawled pages into a massive database, where it serves as crucial training data for their large language models, LLMs. Functionally, a web crawler must be able to crawl the web starting from a given set of seed URLs. And from each web page it successfully crawls, it needs to extract text data and store that text for later processing and analysis.
And for a web crawler, the non-functional requirements are especially critical. Imagine crawling billions of pages, dealing with failures gracefully and, crucially, doing so politely without overwhelming websites.
Indeed, these requirements define the success of a crawler. We assume a massive scale, 10 billion pages on the web, with an average size of 2 megabytes each. Our company needs this entire dataset to be available for training within 5 days of the crawling process starting. Therefore, the system demands fault tolerance to handle failures gracefully and resume crawling without losing any progress. Politeness is absolutely crucial. The crawler must adhere to robots.txt specifications and avoid overwhelming website servers with excessive requests, which could lead to them blocking our crawler. Efficiency is key to completing the crawl of the entire web in under 5 days. And of course, scalability is paramount to handle the sheer volume of 10 billion pages.
Before we go into the high-level components, let's visualize the data flow of a web crawler. It's a continuous loop of discovery and extraction.
Right. The data flow of a web crawler is a cyclical process. It begins by taking a seed URL from its frontier queue. It then requests the IP address for that URL's domain from a DNS server. With the IP, it fetches the raw HTML content from the external web server. Once the HTML is retrieved, it performs 2 critical actions. It extracts the text data from the HTML, and then it extracts any newly linked URLs found within that page. The extracted text data is then stored in a database, typically blob storage. The newly extracted URLs are added back to the list of URLs to crawl our frontier queue, effectively looping back to the first step. This entire sequence repeats until all URLs have been crawled or the defined limits are met.
Building on that data flow, the high-level design involves several key components working in concert. From a queue of URLs to the actual crawling mechanism and storage, each piece plays a vital role.
At a high level, the system features a frontier queue, which manages the URLs awaiting to be crawled. This can be implemented using robust message queuing technologies like Kafka, Redis, or SQS. The crawler component is the workhorse. It fetches web pages, extracts the text data, and importantly, extracts any new URLs found to add back to the frontier queue. DNS servers are essential for resolving domain names into IP addresses, allowing the crawler to actually connect to and fetch content from web pages. The web page itself refers to the external server hosting the content we're crawling, from which the HTML is fetched and text data is extracted. Finally, the extracted S3 text data is where the raw textual content from the web pages is stored. S3 is chosen as our blob storage solution due to its exceptional scalability and durability, which are critical for handling the immense amounts of textual information collected.
Here's where it gets genuinely fascinating, the deep dives. How do you ensure fault tolerance so you don't lose progress on billions of pages? How do you ensure politeness to not crash websites? And how do you scale to such a mind-boggling number of pages to crawl it all efficiently within that tight 5-day time frame?
To ensure fault tolerance and avoid losing progress, the solution is to break the crawler service into smaller pipeline stages. This modularity means if a failure occurs in any single stage, only that specific stage needs to be retried without losing overall progress on the rest of the data. We typically break the crawler service into 2 main stages: the URL fetcher and the text and URL extraction. The URL fetcher stage is responsible for fetching the raw HTML of the web page from the external server. If there's a transient failure, this fetch can simply be retried without losing progress. The raw HTML, once successfully fetched, is immediately stored in durable blob storage like S3 for later processing. The text and URL extraction stage then takes the stored HTML, extracts the relevant text data, and concurrently extracts any newly linked URLs to add back to the frontier queue. We also introduce a metadata DB, which could be DynamoDB, PostgreSQL, or MySQL, with a table that tracks all URLs that have been successfully fetched and processed. This database stores pointers, a link to the blob storage where the raw HTML is stored, and a link to where the extracted text data is stored. This is a crucial anti-pattern avoidance. Storing large, raw HTML payloads directly in the message queue itself is inefficient and expensive, as queues aren't optimized for large blobs. Instead, the queue message will simply contain the ID of the URL entry in our metadata DB, which is much more lightweight.
What happens specifically if the crawler fails to fetch a URL, or if an entire crawler instance goes down mid-process?
If a crawler fails to fetch a URL, we rely on the message queue's built-in retry mechanisms. SQS, Amazon's simple queue service, which we'll use here, supports retries with configurable exponential backoff right out of the box. Initially, messages that fail to process are retried once per the visibility timeout, defaulting to 30 seconds. This visibility timeout then increases exponentially after each retry attempt. For example, 30 seconds, then 2 minutes, then 5 minutes, and up to 15 minutes. After a certain number of failures, determined by the approximate receive count on the message is automatically moved to a dead letter queue, DLQ, preventing it from indefinitely blocking the main queue. If an entire crawler instance goes down mid-process, the URL it was working on will remain in the SQS queue. A message is only removed from the queue when it's confirmed that the URL has been successfully fetched and its HTML stored in blob storage. This way, if a crawler crashes, the URL's message becomes visible again after its visibility timeout expires, and another available crawler will pick it up, ensuring continuous progress. Once the HTML is successfully stored, the crawler deletes the message from the queue, preventing it from being processed again.
Can you compare the suitability of Kafka versus SQS for this specific use case, particularly regarding ensuring no data loss if a crawler fails?
Certainly. With Apache Kafka, messages are retained in a log and are not removed even after they are read. Crawlers track their progress using offsets, which are only updated in Kafka once the URL is successfully fetched and processed. If a crawler fails, the next available crawler simply picks up from the last committed offset, ensuring no data is lost and resuming work exactly where the previous one left off. In contrast with SQS, messages remain in the queue until they are explicitly deleted by a consumer. When a message is fetched by a crawler, a visibility timeout hides it from other crawlers. If the crawler fails before it confirms successful processing, the message automatically becomes visible again after that timeout expires, allowing another crawler to attempt the fetch. Once the HTML is stored in blob storage, the crawler explicitly deletes the message from the queue, ensuring it is not processed again. Given SQS's built-in support for retries and exponential backoff, combined with the ease of configuring visibility timeouts, SQS is a highly practical and effective choice for this system.
Now, a critical ethical and practical consideration. How can we ensure politeness and adherence to robots.txt? We don't want to overwhelm or get banned by websites.
Politeness is absolutely paramount for a web crawler. Our adherence begins with the robots.txt file, which is a standard protocol. This file, hosted on each website, explicitly tells crawlers which pages they are. Disallowed from crawling, and crucially, using the crawl delay directive, specifies how many seconds the crawler should wait between requests to that specific site. Beyond robots.txt, our system will also implement a general rate limiting policy to cap the number of requests made to any single domain. The industry standard and a good rule of thumb is to limit requests to no more than 1 request per second per domain.
What are the specific steps to implement this politeness, incorporating both robots.txt and our own rate limits?
The steps for politeness are: first, we fetch the robots.txt file for the domain we intend to crawl. We parse this file and store its rules, specifically the disallow paths and crawl delay directives in our metadata DB, keyed by domain. When a URL is pulled off our queue, we first check the stored robots.txt rules for its domain. If the URL is disallowed, we simply acknowledge the message in the queue and move on. If it's allowed, we then check the crawl delay directive. If the specified delay time has not passed since our last crawl to that domain, we put the URL back onto the queue with an appropriate delay to respect the crawl delay. If the time has passed, we proceed to crawl the page and immediately update the last crawl time for that domain in our metadata DB.
Beyond just robots.txt, what are the deeper challenges in respecting that 1 domain per second rate limit, especially when you have multiple crawlers all trying to operate in parallel? This sounds like a classic distributed systems problem.
You're right. This introduces significant challenges. Concurrency is a major issue. With N crawlers, multiple instances may attempt to access the same domain simultaneously. We need central coordination to strictly enforce that no more than 1 request per second per domain rule. This often involves a shared, highly available store like Redis to track request counts for each domain. Another, often overlooked problem is the thundering herd. If all crawlers hit a crawl delay or rate limit for a specific domain, they'll all wait for the same duration. Then, when the delay is over, they all try to retry at the exact same instant. This leads to only one succeeding and all the others immediately failing again, resulting in a repeated cycle of retries and contention.
So what's the solution architecture to effectively tackle these concurrency and thundering herd challenges for politeness?
The solution architecture involves a centralized rate limiter, using Redis as our shared data store for coordinating rate limits across all crawlers. We implement a per-domain sliding window. For each domain, we keep a sorted list or counter in Redis to track request timestamps. Before a crawler makes a request, it checks the timestamp of the last request to that domain. If it's less than 1 second ago, the crawler waits and introduces a small random delay, jitter, before retrying. If it's 1 second or more, it proceeds and updates the timestamp in Redis. Redis commands like getSetWithExpiry or zadsRangeByScore can manage this window. Crucially, to prevent the thundering herd and avoid synchronization, we introduce jitter. Jitter means adding a small random delay, typically between 100 to 300 milliseconds before retrying a request. Without jitter, all crawlers wait for exactly 1 second, then retry simultaneously, leading to repeated failures. With jitter, each crawler delays by a slightly random amount, spreading out the retries and significantly reducing contention, allowing more requests to succeed on subsequent attempts. For example, a simple sleep random.uniform 0.1, 0.3 would introduce this random delay.
Now, the ultimate scalability challenge. How do we scale to 10 billion pages and efficiently crawl them in under 5 days? This clearly demands massive parallelization.
To achieve the ambitious goal of crawling 10 billion pages in under 5 days, parallelization is not just an option, it's an absolute necessity due to I/O limits. Let's do a quick estimate. If each page averages 2 MB in size, and we're provisioning AWS instances that provide, say, 400 GBps of network throughput with a realistic 30% usable throughput, that translates to approximately 7,500 pages per second per instance. Therefore, to crawl 10 billion pages at 7,500 pages per second, a single machine would take roughly 15.4 days. To meet our aggressive 5-day deadline, we would need to divide 15.4 days by 4 machines, yielding approximately 3.85 days. This estimate shows we can meet our goal. It's important to remember that this is an estimate. Thorough load testing would be required for precise accuracy, but the core reasoning for parallelization is key in system design discussions.
What are some potential bottlenecks that might be easily overlooked in such a large-scale crawling operation? Perhaps something like DNS.
DNS is indeed a common, often overlooked bottleneck. To mitigate this, we can implement DNS caching directly within our crawlers. This significantly reduces the number of external DNS requests our system needs to make, as all subsequent URLs from the same domain will reuse the same cached DNS lookup. Additionally, we can configure our system to use multiple DNS providers and employ a round-robin strategy between them. This helps distribute the load across various providers and reduces the risk of hitting rate limits imposed by any single DNS service.
How do we avoid wasting precious time and resources recrawling pages that have already been processed? This could be a huge efficiency drain on billions of pages.
To avoid recrawling pages, we have 2 primary solutions. First, content hashing. When a page is fetched, we compute a hash of its content, for example, an MD5 or SHA-256 hash. This hash is then stored in our URL table within the metadata DB. When a new URL is considered, we fetch its content, hash it, and compare it to the hashes already in our metadata DB. If a match is found, we know it's a duplicate and can skip processing that page. To make this lookup fast, we build an index on the hash column in the metadata DB for quick retrieval.
And what's the second option for avoiding recrawling, perhaps a more probabilistic approach for massive scale?
The second option is to use a Bloom filter. A Bloom filter is a probabilistic data structure that efficiently tests whether an element is a member of a set. It can definitively tell you if an element is not in the set, but it can only tell you with some probability if an element is in the set. We would use a Bloom filter to store the hashes of the content of all pages we've already crawled. When a new URL is fetched, we hash its content and check the Bloom filter. If the hash is not in the Bloom filter, we're certain it's a new page. If it is in the Bloom filter, it has likely been crawled before, and we can then skip it. Redis can be used to store the Bloom filter as it has a built-in data structure for this. The main trade-off and challenge with a Bloom filter is that it can produce false positives, meaning it might occasionally indicate a page was crawled when it wasn't. However, it never produces false negatives, guaranteeing that we won't accidentally recrawl a page we truly intended to skip.
Finally, we need to talk about crawler traps. These are tricky situations where a crawler can get stuck in an infinite loop of links. How do we prevent that?
To effectively guard against crawler traps, which can exhaust resources by leading the crawler into infinitely deep or recursive link structures, we implement a maximum depth for our crawlers. We add a depth field to our URL table in the metadata DB. Each time a link is followed to a new page, we increment this depth field. If the depth exceeds a predefined threshold, for example, 5 or 10 levels deep, we stop crawling that page and any links from it. This prevents the crawler from getting caught in dynamically generated content loops, calendar traps, or recursive directories.
Let's move to ubiquitous communication, WhatsApp. Billions of messages exchanged daily across group chats, with media, and even when you're offline. What are the core functional requirements for such a massive messaging platform?
For a messaging app like WhatsApp, the functional requirements are fundamentally about enabling seamless communication. Users should be able to start group chats with multiple participants, typically with a limit, say, of 100 users. Users must be able to send and receive messages instantly. Crucially, users should be able to receive messages sent while they are not online, with a reasonable retention period, perhaps up to 30 days. And finally, users should be able to send and receive media, like photos, videos, or voice notes, within their messages.
For a real-time messaging app, the non-functional requirements are incredibly stringent. We're talking low latency, guaranteed deliverability, and extreme scalability across billions of users. And given the sensitive nature of messages, careful consideration of their storage and privacy is also vital.
That's absolutely right. Messages must be delivered to available users with low latency, ideally under 500 milliseconds, for a truly real-time feel. The system needs to guarantee deliverability of messages. They absolutely must make their way to the intended recipients. It needs to handle billions of users with high throughput, which we'll delve into in scale estimation. Messages should be stored on centralized servers no longer than necessary, balancing deliverability with privacy and storage efficiency. And finally, the system must be resilient against failures of individual components, ensuring continuous service even if parts of the infrastructure experience issues.
What are the fundamental pieces of information that a messaging app like WhatsApp needs to manage? The core entities that make all those conversations possible.
The core entities for a messaging app are quite focused. We have users, the individuals interacting with the system. Chats represent the conversations, designed to support anywhere from 2 up to our 100 user limit. Messages are the actual content exchanged within these chats, text, media, etc. And importantly, clients, acknowledging that a single user might have multiple devices, for example, phone, tablet, web, all connected to the service simultaneously.
Unlike many other services that rely on simple request response, a chat app leans heavily on bidirectional persistent communication. This immediately points us to the choice of WebSockets for APIs and specific mechanisms for confirming message delivery.
Yes, precisely. For a chat app with its high frequency of both sending and receiving updates, a traditional REST API is generally not appropriate. This is a perfect use case for a bidirectional socket connection, namely WebSockets. The APIs would include calls to create a chat, send messages on the chat, create attachments for media, and remove users to the chat. What's key is that each of these commands, once processed by the server, will have parallel new message or chat updated commands sent to other clients in the conversation. Crucially, when a command or message has been successfully received by a client, that client will send an acknowledgement command back to the server. This explicitly tells the server the message has been delivered to the client and no longer needs to be held or retried. By forcing clients to act, the system can know for certain that the message has been delivered all the way to the client device, not just to the server. This also implies corresponding APIs for when a chat is created or updated and when a message is received by a client.
Let's trace the high-level design now. How do you create a group chat? How are messages sent, ensuring both online and offline delivery? And how is media handled within messages?
Okay, to begin with users being able to start group chats with multiple participants, up to 100. We start with a simple service located behind an L4 load balancer, necessary for WebSocket support, which can write chat metadata to a database. DynamoDB is an excellent choice here for its fast key value performance and scalability, though other options exist. The steps are: a user connects to our service and sends a create chat message. The service, within a database transaction, first creates a chat record in the database. Simultaneously, it creates a chat participant record for each user invited to that chat. The service then returns the new chat back to the user. For the chat participant table, we need 2 primary access patterns, looking up all participants for a given chat and looking up all chats for a given user. This is sufficiently done with a composite primary key on chatted and participanted fields. A range lookup on chatted provides all participants for a given chat. To support looking up all chats for a given user, we'll need a global secondary index, GSI, with participanted as the partition key and chatted as the sort key. DynamoDB automatically keeps this GSI in sync with the base table, allowing for efficient querying of all chats associated with a particular user.
Now, the core functionality. Sending and receiving messages, and the critical requirement of receiving messages sent while users are not online, up to 30 days of retention. How does that flow?
For sending and receiving messages, including offline delivery, the process for sending a message starts when a user sends a send message to the chat server. The chat server first looks up all participants in that chat via the chat participant table. Then the chat server initiates a database transaction that simultaneously performs two crucial rights. A, it writes the message content itself to the message table, and B, it creates a new entry in the inbox table for each recipient of that message. The chat server then immediately returns a success or failure status to the sending user, along with the final message of it. After that, the chat server attempts to deliver the message. It looks up the WebSocket connection for each participant who is currently online and attempts to deliver the message to them via a new message command. For these connected clients, upon successful receipt, the client will send an ACK message back to the chat server indicating they've received the message. The chat server then immediately deletes that message from the inbox table for that specific client. Now, for clients who aren't connected at the time, the messages remain in their respective entries in the inbox table. Once the client connects to our service later, the system will automatically look up that user's inbox and find any undelivered message IDs. For each of those message IDs, it will retrieve the full message content from the message table. These messages are then written to the client's newly established WebSocket connection via the new message command. Again, upon successful receipt, the client sends an ACK message back to the chat server, and the chat server then deletes that message from the inbox table. Finally, to manage storage and comply with retention policies, the system will need to periodically clean up old messages in both the inbox and message tables. This can be done with a simple cron job that deletes messages older than, say, 30 days.
How are users able to send and receive media in their messages? Handling large files securely and efficiently in a chat context is a specific challenge.
For users to send and receive media in their messages, we offload the direct file transfer to optimize our chat servers. Users are typically given permission, for example, via pre-signed URLs, to upload their media files directly to a scalable blob storage service like S3. As an example, a user might first send a getAttachmentTarget message to the chat server, which securely generates and returns that pre-signed URL. Once the media file is successfully uploaded to S3 by the client, the user's client will have a URL pointing to this attachment. This URL is then sent to the chat server as an opaque URL within a regular chat message. While a CDN, Content Delivery Network, could be placed in front of the blob storage to cache media, given our cap of 100 participants per group, the cache benefits are likely to be relatively small compared to platforms with truly viral public content.
Now, the truly difficult deep dives for a service like WhatsApp. How do you scale to billions of simultaneous users? And how do you handle users having multiple devices, all needing to receive the same messages consistently? These are monumental challenges for a global real-time platform.
Let's tackle how we handle billions of simultaneous users. Our primary strategy involves scaling out the number of chat servers. However, simply adding more servers introduces a new problem. Now, the sending user and the receiving users might be connected to completely different chat server instances. If user A sends a message to user B and user C, but user B is on chat server 1 and user C is on chat server 2, how do we get the message to both? The solution is to integrate a purpose-built system for bouncing messages between servers, commonly known as a pub-sub-publish-subscribe system.
Can you walk through how that pub-sub system would work during connection and when a message needs to be sent, ensuring cross-server delivery?
Okay, on connection. When a user connects to any of our chat servers, that server immediately connects to the pub-sub system to subscribe to a unique topic for that specific user ID. Any messages received on that subscription for that user ID are then automatically forwarded to the user's active WebSocket connection. When a message needs to be sent, the chat server that received the send message command from the sending user takes that message and publishes it to the pub-sub topic for each relevant user ID, i.e. all recipients. This published message is then received by all chat servers that are subscribed to those respective user ID topics. Those chat servers then forward the message to the corresponding user's WebSocket connection. It's worth noting that while pub-sub systems are typically at most once delivery, meaning a message could be lost if there are no active subscribers, this is acceptable in our design because the durability of messages is already managed by our inbox table. If a message is missed via pub-sub, the inbox table ensures it's delivered later. One additional complexity is that there will be an all-to-all relationship between our chat servers and our Redis cluster servers, meaning we'll need connections from each chat server to each Redis server.
What do we do to handle multiple clients for a given user? So if I'm on my phone, tablet, and desktop, how does that message show up on all three simultaneously and consistently?
To handle multiple clients for a given user, we need to extend our data model and delivery mechanism. First, we'll create a new clients table in our database, specifically to keep track of each active client device associated with a user ID. When our system looks up participants for a chat, it will now also need to look up all of the clients associated with each user in that chat. Our inbox table will need to be updated to be per client rather than per user. This means each individual client device, phone, tablet, desktop, will have its own entry in the inbox table for undelivered messages. When a message is sent, it will now need to be sent to all of the clients for that user, not just the user generally. On the pub/sub side, nothing fundamentally changes. Chat servers will continue to subscribe to a topic based on the user in it. To prevent unbounded growth in storage and throughput due to an excessive number of devices, it's wise to introduce some limits, for instance, capping a user account to 3 active clients simultaneously.
From private conversations, let's swing to public opinions. Yelp, the go-to for finding and reviewing local businesses. It's a fascinating blend of search, user-generated content, and community. What are the core functional requirements a Yelp-like system needs to fulfill?
For a local business review site like Yelp, the functional requirements are quite clear. Users need to be able to search for businesses using various criteria: by name, by geographical location, latitude and longitude coordinates, and by category. Users also need to be able to view businesses and their associated reviews, which is fundamental for discovery and decision-making. And crucially, users must be able to leave reviews on businesses, which requires a mandatory 1 to 5-star rating and allows for an optional text component.
For a service centered on search and user-generated content, the non-functional requirements are incredibly important. Low latency search, high availability, and massive scalability are critical. Consistency, interestingly, is often eventual here, allowing for a better user experience on a predominantly read-heavy platform.
That's absolutely correct. The system must achieve low latency for search operations, ideally under 500 milliseconds, as users expect instant results. It must be highly available, meaning users can almost always access the platform, even if there are minor data inconsistencies, as eventual consistency is acceptable here. Unlike a banking transaction, a review or rating doesn't need to be immediately consistent across all replicas globally. And crucially, the system must be scalable to handle a significant load: 100 million daily users and 10 million businesses.
What are the fundamental pieces of information, the core entities that define the Yelp ecosystem? These are the building blocks for all the interactions.
The core entities are straightforward for Yelp. The business entity represents a local business or service listed on the platform. It includes details such as its name, precise location, category, and its dynamically calculated average rating. The user entity represents a Yelp user who actively interacts with the platform, whether by searching for businesses or leaving reviews. And finally, the review entity represents a specific review submitted by a user for a business, encompassing both the numerical rating and any optional text commentary.
The APIs or system interfaces for Yelp are all about searching for information, retrieving business details, and of course enabling users to share their opinions through those crucial reviews.
Precisely. We need an API to search for businesses, typically a GET businesses endpoint. A crucial design consideration for any endpoint returning a large set of results is pagination. This minimizes the payload size returned to the client and makes the system more responsive by only sending a manageable chunk of data at a time. To view business details and reviews, we typically separate these into 2 related endpoints: get tbusinesses.businessID to fetch the core business details, and gtbusinesses.businessID reviews to retrieve the reviews specific to that business. Finally, to leave review, a POC businesses.businessID reviews endpoint allows users to submit their rating and optional text.
Let's outline the high-level design now. How do users search for businesses? How do they view detailed information in reviews? And how is the process of leaving a review handled at a high level?
Okay, for users to search for businesses. When a user initiates a search, their client sends a GET request to businesses, including search parameters as optional query parameters. For example, name, pizza, and location, Nukak. Our API gateway routes this request to the business service. The business service then queries its underlying database, applying the search criteria to retrieve relevant business listings. These results are then returned to the client via the API gateway.
And how about when users want to view businesses and their reviews? What's the high-level flow for that?
For users to view businesses in their reviews, the business service will query its database for the specific business details first. For simplicity in this high-level design, we'll initially keep the reviews in the same database as the businesses, requiring a join operation between the two tables. When a user sends a JECI request to businesses.businesswhile, the API gateway routes this to the business service. The business service retrieves both the business details and its associated reviews from the database, then combines this information and returns it to the client.
A common question in system design is when to separate services. What's the rationale for keeping business viewing and searching logic as part of the same service for now?
That's an excellent question, as there's no hard and fast rule for service separation. The main criteria are A, whether the functionality is very closely related, and B, whether the services need to scale independently due to vastly different read-write patterns. In this case, viewing a business and searching for a business are intimately related from a user's perspective, and crucially, the read patterns are quite similar, both are read-heavy. So for now, it makes perfect sense to keep this logic consolidated within the same business service, reducing complexity.
And what about the process of leaving reviews? Does that warrant its own distinct service, and why?
For users to leave reviews on businesses, we introduce a new, distinct service, the review service. This service is specifically designed to handle the creation and management of reviews. The primary reason for separating this into its own service is that the usage pattern is significantly different from searching or viewing businesses. Users search and view businesses constantly, but they leave reviews far less frequently. When a user submits a review, their client sends a POST request to businesses.business-id reviews with the review data. The API gateway routes this to the review service. The review service then stores the review data in its own dedicated database, and a confirmation is sent back to the client.
Now, let's get into the deep dives. How do you efficiently calculate and update average ratings for businesses, ensuring they're always readily available in search results? How do you guarantee a user can only leave one review per business? And how do you handle complex search queries, especially those involving location and categories, efficiently? These are critical challenges for a platform like Yelp.
Calculating the average rating on the fly for every search query would be terribly inefficient and impractical at scale. The solution is to update the average rating as new reviews are received, rather than relying on a periodic cron job. A first thought might be to introduce a new column, num reviews, into the business table. Then, to update an average rating, you could simply calculate old rating num reviews plus new rating, num reviews plus 1. This is a numerically cheap calculation, requiring just a few CPU cycles, so it could theoretically be done synchronously for each new review.
What's the potential issue or pitfall with that simple synchronous update approach for the average rating, especially if multiple reviews come in quickly?
The crucial issue is concurrency. What happens if multiple reviews for the same business come in at the exact same time? One update could easily overwrite another, leading to an inconsistent or inaccurate average rating. The refined solution is to use optimistic locking. Optimistic locking is a technique where you first read the current state of the business, including its old rating and num reviews. Then, when you attempt to update it, you include a condition that checks if the state, for example, the num reviews, has changed since you initially wrote it. If the state has changed, your update fails, and you typically retry the operation. While a version number is often added to the table for locking, simply checking if the number of views has changed can be sufficient here.
Is there an over-engineered solution for average rating updates that we should highlight to avoid, perhaps involving message queues? And what's the broader insight about simple solutions here?
Yes, an over-engineered solution would be to introduce a message queue where incoming reviews are written to it, and then a separate consumer service updates the average rating asynchronously. While that might be appropriate for other scenarios, it introduces unnecessary complexity for this specific problem. Here's the important insight. Many people search and view businesses, but very few actually leave reviews. The read-to-write ratio can be as high as 1,000.1. With 100 million daily users, that would mean only about 100,000 writes reviews per day, or roughly 1 write per second. This is a tiny volume. Modern databases can handle thousands of writes per second, so even accounting for surges, this average rating update will almost never be a problem. Calling out this simplicity and the lack of need for an overly complex solution is often the hallmark of a staff-level candidate and demonstrates a deep understanding of where engineering effort is truly needed.
Next, a critical data integrity constraint. How would you modify your system to ensure that a user can only leave one review per business? This feels like it should be enforced at the lowest possible level.
You're absolutely right. This constraint should be enforced via a database constraint, not via an application layer check. The reasoning is simple. An application layer check is susceptible to consistency issues. If the same user simultaneously submits two reviews for the same business, it's entirely possible for both requests to pass the application level check before the first one is committed to the database. This would result in two reviews, violating our constraint. The core principle here is, whenever a data constraint needs to be enforced, you should enforce it as close to the persistence layer as possible. This ensures your business logic is always consistent and avoids having to do extra complex work in the application layer to maintain that consistency.
For Yelp, complex search queries are paramount. How can you improve search to handle those more efficiently, especially when users are filtering by location, name, and category simultaneously?
To handle complex search queries efficiently, we recognize that we need three distinct indexing strategies to support our three very different types of filters. For location, to efficiently search by geographic coordinates, we need a geospatial index, such as geohashes, quad trees, or R trees. For name, to efficiently search by business name, which often involves partial matches or keywords, we need a full-text search index, which typically employs inverted indexes to quickly locate terms within documents. For category, like Italian restaurant or coffee shop, a simple B-tree index on the category field is usually sufficient. Several technologies can support all three of these indexing strategies, with Elasticsearch being a common and powerful example. Elasticsearch excels at various geospatial indexing methods, geohashing quad trees, R trees, making location-based searches highly efficient. It also offers robust full-text search capabilities and is well-suited for category filtering, making it ideal for multifaceted search requirements.
What are the cons of using Elasticsearch as a primary database, and how do you ensure data synchronization if it's acting as a secondary search index?
While Elasticsearch is phenomenal for search, it has cons if used as a primary database. It's not optimized to maintain transactional data integrity with full ACID, atomicity, consistency, isolation, durability, compliance, nor can it handle complex, multi-statement transactions in the way a relational database can. Its fault tolerance, while effective, requires careful configuration to avoid potential data loss during node or network failures. As a result, when using Elasticsearch as a search index, we need a robust way to ensure that its data remains in sync, consistent with our primary transactional database. The best way to achieve this is by using a change data capture CDC system. CDC captures all changes, inserts, updates, deletes from our primary database, and then reliably applies them to the Elasticsearch index in near real time.
Is there another solution for complex search, perhaps one that allows us to avoid introducing an entirely new service like Elasticsearch and keeps all our data in a single database technology?
Yes, absolutely. One way to avoid the consistency issues and the operational overhead of a separate search service altogether is to leverage a powerful relational database like PostgreSQL with its appropriate extensions enabled. PostgreSQL has a robust geospatial extension called PostGIS that can be used to index and query geographic data with great efficiency. It also has a powerful full-text search extension called PGTRGM for trigram matching that can be used to index and query text data, supporting fuzzy matching. By using these extensions, we can create a geospatial index on the latitude and longitude columns and a full-text search index on the business name and description columns, all within our existing PostgreSQL database, without needing to introduce a new service or manage data synchronization. However, it's worth noting that while PostGIS is excellent for geospatial queries, PGTRGM or native PostgreSQL full-text search might not perform as well as a dedicated search engine like Elasticsearch for very large-scale full-text search scenarios.
When designing a geospatial search without a specialized search engine like Elasticsearch, what are the key aspects or strategies that interviewers typically focus on?
When designing a geospatial search without Elasticsearch, interviewers typically focus on three key aspects. First, the geospatial indexing strategy. You need to choose an efficient way to index geographic points. Common options include geohashing, quad trees, or R trees. For instance, quad trees are often well suited for infrequent updates and clustered data, as seen in dense urban areas like New York City. Second pass filtering. After an initial rough selection using the index, you use a more precise calculation, such as the Haversine formula, to calculate the exact distances between the user's coordinates and the business coordinates. This step precisely filters out any results that fell just outside the desired radius but were included by the index's approximation. Third, query sequencing. You should apply the distance filter first to dramatically reduce the search space. Then you apply other criteria like name or category filters on that much smaller, already distance filtered result set, leading to much more efficient overall query execution.
How would you modify your system to allow searching by predefined location names, such as cities or neighborhoods, not just a simple radius from a point. Users often search for pizza in NYC or coffee in the Mission.
Our current design supports searching based on a business's precise latitude and longitude. However, users naturally search using more common terms like city names or neighborhood names, for example, pizza in NYC. These can also be more complex, like a specific neighborhood such as the Mission in San Francisco. A simple radius from a center point is insufficient for this use case because cities and neighborhoods are not perfectly circular. They can have wildly irregular and complex shapes. The solution is to define a polygon for each name's location and then check if any of the businesses are located within that specific polygon. This requires two things: going from a location name to its corresponding polygon, and then using that polygon to filter a set of businesses efficiently.
So we need to map location names to polygons and then filter businesses by those polygons. How do we approach these two distinct steps to enable searching by predefined location names?
To enable searching by predefined location names, we first map location names to polygons. We create a dedicated locations table in our database. This table would contain columns for name, e.g. San Francisco, Brooklyn, type, for example, city, neighborhood, and a polygon column that stores the geographic shape, perhaps using GeoJSON format or a list of coordinates obtained from public geographic data sources like GeoAppify. We'd index the name column for fast lookups. Second, to filter businesses by polygon. We need a database or search engine with robust geospatial support, such as Postgres with PostGIS or Elasticsearch with its GeoShape query capabilities. Instead of running a complex GeoShape or GeoBounding box query per incoming request, a more efficient approach is to pre-compute which predefined locations each business falls within during its creation or update. We then store these as location names, for example, a list of strings or enums like San Francisco, Mission District, directly in the business record. For implementation with Elasticsearch, we would add this location names field to the business document. We then create an inverted index on this location names field using Elasticsearch's keyword type for highly efficient filtering. This way, we query businesses by simply matching the location names against the polygon's identifier from our locations table. This approach avoids costly real-time geospatial polygon queries by pre-computing location memberships, enabling fast and scalable searches by city or neighborhood.
Finally, let's cap off our deep dive with a true behemoth: YouTube or any video streaming platform. It's not just about hitting play, it's about uploading massive files, transcoding them for various devices, and delivering seamless streams globally. What are the absolute core functional requirements for such a platform?
The core functional requirements for a video streaming platform are surprisingly simple on the surface, yet lead to immense complexity. First and foremost, users must be able to upload video content to the platform. This is the genesis of all content. And equally critical, users must be able to watch or stream videos seamlessly, irrespective of their device or network conditions.
And the non-functional requirements for video streaming are particularly challenging. High availability, handling massive video files, low latency streaming even with poor bandwidth, and extreme scalability are critical for a truly global platform.
Absolutely. High availability is crucial. We must prioritize availability over strict consistency to ensure the system is always accessible and videos can be streamed. The system needs to support very large videos, handling uploads and streaming of files that can be tens of gigabytes in size. Low latency streaming is essential to enable smooth, buffer-free playback, even in low bandwidth environments. Scalability is paramount, supporting approximately 1 million videos uploaded per day and around 100 million videos watched per day globally. And critically, resumable uploads are a must, allowing users to pause and resume large video uploads without any data loss, which is vital given potentially unreliable network conditions.
What are the core pieces of information, the core entities that a video streaming platform needs to manage? Beyond just users and video files, there's crucial metadata for every piece of content.
The core entities for a video streaming platform begin with the user, representing either an uploader or a viewer. The video itself is the actual media file that is uploaded or consumed, and crucially, video metadata, which encapsulates all the associated information about a video. This includes the uploading user, video title, description, upload date, duration, a URL reference to a transcript if available, a URL to the primary manifest file in S3, which points to all the different video formats, and for resumable uploads, a list of chunks, including each chunk's fingerprint and its current status.
And how do clients interact with the system for uploads and streaming? The APIs or system interfaces abstract away a lot of complexity, often leveraging powerful cloud storage features.
Yeah, for uploads, the API endpoint is typically a POS upload. The client's request payload for this endpoint only contains the video's metadata, title, description, etc. In response, the server generates and provides a pre-signed URL to the client. The client then uses this pre-signed URL to upload the large video file directly to a cloud blob storage service like S3, leveraging S3's multi-part upload capabilities for efficiency. The video metadata itself is separately stored in our database. For streaming, the API endpoint is a GET videos video wide. This endpoint returns the video metadata for the requested video. Crucially, this metadata includes a URL pointing to the primary manifest file in S3, which the client then uses to initiate and manage the video stream.
Before we jump into the high-level design, let's quickly define a few key terms that are absolutely fundamental to understanding how video streaming works, especially when it comes to quality and delivery.
Certainly. First, a video codec is a technology used to compress and decompress digital video. Its purpose is to make video files much smaller for efficient storage and transmission over networks while still maintaining acceptable quality. Then there's byte rate, which is the number of bits transmitted over time, typically measured in kilobits per second, kbps, or megabits per second, mbps. A higher byte rate generally means better video quality, but results in a larger file size and requires more bandwidth. Finally, manifest files are crucial for modern streaming. The primary manifest file is like a table of contents for a video. It lists all the available versions of a video, different formats, resolutions, and byte rates. Media manifest files are individual index files that list the URLs to specific video segments, and these are what video players actively use to stream the content.
Now let's assemble the high-level design for a video streaming platform. This involves both the upload pipeline, including all the post-processing for different formats, and the seamless streaming experience for viewers.
Okay, for users to upload videos, the core approach is that video files are uploaded directly to a blob store like S3. We achieve this securely and efficiently via pre-signed URLs and by leveraging multi-part upload capabilities for large files. The video metadata itself is stored in a highly available and scalable database like Cassandra, with data partitioned by video wide for efficient individual video queries. Upon successful completion of each chunk upload to S3, S3 triggers event notifications, which are consumed by an AWS Lambda function. This Lambda function then updates the video metadata in Cassandra, recording the progress of the upload. The overall process is the client sends an initial post-upload request with only the video metadata. The server generates a pre-signed URL for the direct S3 upload and stores that initial metadata in Cassandra. The client then streams the video data directly to S3 using the pre-signed URL. Once the full video is in S3, the post-processing pipeline begins. First, the original video is split into small playable segments, typically a few seconds each. Next, each of these segments is transcoded. This means converting them into multiple formats using different codecs, resolutions, for example, 480p, 720p, 1080p, and byte rates. This ensures compatibility with a wide range of devices and network conditions. Finally, the system generates manifest files. It creates a primary manifest file that lists all the available video formats and resolutions. Concurrently, it creates media manifest files that specifically reference the URLs to each of the generated video segments stored in S3. The output of this entire pipeline is the actual video segment files in their different formats, all stored in S3, along with the primary and media manifest files also stored in S3.
And once all that processing is done, how do users then watch these videos? What's the approach for delivering that seamless, low-latency streaming experience?
For users to watch videos, the approach centers around adaptive byte rate streaming, which is key for efficient, low-latency playback. The steps are: the client sends a JTB video wide request to fetch the initial video metadata. This video metadata contains a crucial URL pointing to the primary manifest file in S3. The client then downloads this primary manifest file. Next, the client dynamically selects the optimal video format, resolution, and byte rate based on its current network conditions, the type of device it's running on, and any user quality settings. The client then retrieves the segment URLs from the appropriate media manifest file and downloads the very first segment. The client immediately begins playing that first segment while simultaneously downloading subsequent segments in the background. A critical feature is that if network conditions change, for example, if the bandwidth drops, the client automatically adapts by requesting and downloading future segments in a more compressed, lower resolution format. This ensures uninterrupted playback, prioritizing continuity over pristine quality when bandwidth is limited.
Now for the truly intricate deep dives. How do you handle resumable uploads for those massive files, ensuring users don't lose progress? How do you scale for 1 million uploads and 100 million views a day? And what are the crucial additional considerations that tie this entire complex system together?
For resumable uploads, which are vital for large files and potentially unstable networks, the approach is designed for robust recovery. First, the client divides the video into smaller chunks, typically 5–10 megabytes each, and generates a unique cryptographic fingerprint, a hash for each chunk. The client then sends an initial post-upload request to our server, updating the video metadata in Cassandra. This metadata now includes a list of all these chunks, each with its fingerprint and an initial status of not uploaded. The client then uploads each chunk independently to S3 using multi-part upload via pre-signed URLs. S3 is configured to trigger event notifications, which are processed by an AWS Lambda function upon successful completion of each chunk upload. This Lambda function then updates the video metadata in Cassandra, marking that specific chunk's status as uploaded based on its unique fingerprint. If the upload process is interrupted at any point, e.g. network disconnect, app crash, when the user resumes, the client first fetches the video metadata from Cassandra. By comparing its locally stored chunk fingerprints with the uploaded statuses in the metadata, the client can identify precisely which chunks have already been uploaded and then resume the process by skipping those already completed chunks, saving time and bandwidth.
That's very clever for handling large files and interruptions.
Yeah.
What about the sheer scalability for high volume? Specifically handling 1 million uploads and 100 million views per day, how are the different services designed to meet that demand?
For scalability for high volume, 1M uploads, 100 views per day, each component is designed for horizontal growth. The video service itself is a stateless service, primarily handling HTTP requests for pre-signed URLs and video metadata queries. It's designed to be horizontally scalable, with a load balancer distributing incoming traffic evenly across multiple instances. The video metadata is stored in Cassandra, specifically chosen because it scales horizontally through leaderless replication and consistent hashing. Data is partitioned by video wide to ensure uniform distribution and efficient individual video queries. The video processing service, responsible for post-processing tasks like splitting, transcoding, and manifest generation, operates using a distributed task queue, for example, AWS, XQS, or Kafka. This allows it to handle bursts in video uploads by distributing the directed acyclic graph of data of processing work across a pool of worker nodes, scaling out as needed. S3 serves as the highly scalable blob storage for all video segments and manifest files. It's inherently designed to handle incredibly high traffic and massive file volumes efficiently.
How do you handle hot videos? Those that suddenly go viral and attract immense traffic and ensure low latency for users across the globe.
To effectively handle hot videos, we take proactive measures within Cassandra. We tune it to replicate popular video metadata across multiple nodes. This ensures that the load for highly requested metadata is distributed, preventing a single point of contention. Additionally, we implement a cache, like Redis or Memcached, to store frequently accessed video metadata for even faster retrieval, often serving it directly from memory. For low latency for global users, we employ a robust network of content delivery networks, CDNs. CDNs cache video segments and manifest files geographically much closer to users. This dramatically reduces latency for viewers who might be thousands of miles from our main S3 data centers, ensuring a consistently smooth streaming experience worldwide.
Beyond the core design, what are some crucial additional considerations for building and maintaining a production-grade video streaming platform?
Several additional considerations are vital. For security, we use pre-signed URLs with carefully managed expiration times for secure S3 uploads and downloads. We also rigorously authenticate and authorize users for all upload and streaming actions. Regarding streaming protocols, common industry standards like HLS, HTTP live streaming, and DHH, dynamic adaptive streaming over HTTP, are essential. They inherently handle video chunking and adaptive bitrate streaming to optimize delivery. Monitoring and logging are non-negotiable. We track comprehensive upload and streaming metrics, example, success rate, latency, errors, for continuous performance optimization. We also log failures throughout the post-processing pipeline for efficient debugging. For error handling, we implement robust retry mechanisms for failed chunk uploads or transcoding tasks, often with exponential backoff. Crucially, we notify users of any upload or streaming failures with clear, actionable error messages. Finally, cost optimization is a significant concern. We use S3 lifecycle policies to automatically move older, less accessed videos to cheaper storage tiers, like S3 Glacier. We also optimize our transcoding processes to balance video quality with the associated storage and processing costs, ensuring efficiency without sacrificing too much user experience.
Wow. We just took a truly extensive deep dive into the system designs of some of the most influential applications out there. From the high-stakes world of Ticketmaster's bursty event booking to the global scale of YouTube's video streaming, we've systematically unpacked the functional needs, wrestled with formidable non-functional demands, and marveled at the ingenious deep dives that solve truly complex, real-world engineering problems.
If we connect this to the bigger picture, what stands out consistently across all these systems is the delicate yet powerful act of balancing trade-offs, whether it's consistency versus availability or exactness versus approximation. And of course, it's the skillful leveraging of a powerful toolkit of distributed systems like Redis, Kafka, and Elasticsearch. It highlights how seemingly simple user interactions are built upon layers of incredibly sophisticated hidden engineering.
It really does give you a new appreciation for the digital world we inhabit. Every tap, every swipe, every stream is orchestrated by a symphony of services meticulously designed for scale, resilience, and speed. So what does this all mean for you? Next time you use one of these apps, perhaps you'll think about the hidden complexity and the brilliant minds that designed it. And maybe, just maybe, it will inspire you to dive even deeper into the world of how things are built.
This raises an important question. As these systems continue to evolve with new demands and ever-increasing scale, what will be the next frontier in engineering challenges, and how will the architects of tomorrow continue to innovate, adapting these principles to entirely new paradigms?
A perfect thought to leave you with until our next deep dive. Thanks for joining us, and keep exploring.